Hello there. You're listening to Science Blanket, your quiet space for wonder. I'm so glad you've joined me tonight. Tonight, we are wrapping ourselves in the story of our solar system. It is a vast and quiet neighborhood held together by the gentle, golden pull of the sun. Think of it not as a complex machine of gravity and speed, but as a family of worlds, each with its own rhythm, drifting together through the velvet dark of space. As we begin, imagine yourself floating lightly among the distant stars. You aren't here to study the distances or the math of the orbits. You are just here to wander through the stillness. Feel the coolness of the deep dark and the soft, distant glow of the sun as it touches the edge of each world. Now, take a deep breath. Feel the mattress beneath you, holding you just as surely as gravity holds the planets in their places. Let your feet grow heavy, release the tension in your jaw, and let the worries of the day drift away like a falling star. Give yourself permission to be still, and let the quiet of the universe settle over you. Let's explore our solar system together. The solar system formed about 4.6 billion years ago from a vast, rotating cloud of gas and dust suspended in the emptiness of space. This cloud, perhaps disturbed by the shockwave of a nearby supernova or simply reaching a critical density through its own slow accumulation, began to collapse inward under the relentless pull of gravity. As the cloud contracted, it spun faster, flattening into a disk shape with most of the material drawn inexorably toward the center. This was the birthplace of our sun and everything that orbits it today, a transformation that took millions of years to unfold in the silent darkness of the early solar system. We know this age with remarkable precision thanks to radiometric dating of meteorites that fall to Earth. These ancient rocks are among the oldest solid materials in the solar system, preserving within their mineral structures the chemical signatures of that original collapsing cloud. By measuring the decay of radioactive isotopes locked inside these meteorites, scientists can work backward through time, calculating when these first solid grains condensed from the swirling gas. The ages cluster consistently around 4.6 billion years, giving us a timestamp for the moment when our cosmic neighborhood began to take shape. These meteorites are time capsules, carrying messages from an era long before planets existed. As the cloud continued its gravitational collapse, an extraordinary sorting process began. The vast majority of the material, perhaps 99% of the total mass, was drawn into the growing protosun at the center of the disk. The remaining material, spread throughout the flattened disk surrounding the young star, would become everything else we see today. The 8 planets, their many moons, the asteroids, comets, and all the smaller bodies that populate the solar system. This disk was a churning environment of collisions and accretion, where tiny dust grains stuck together through static electricity and gentle impacts, gradually building into pebbles, then boulders, then planetesimals miles across. Over millions of years, these growing bodies swept up more and more material from their orbital neighborhoods, eventually forming the worlds we know. The early sun's heat created a crucial dividing line in this protoplanetary disk, located at about 5 astronomical units from the center, roughly where Jupiter orbits today. This boundary, known as the frost line or snow line, marked the distance beyond which water and other volatile compounds could condense into solid ice. Inside this line, closer to the sun, temperatures were too high for ice to form, and only rocky materials and metals could remain solid. This is why the inner planets, Mercury, Venus, Earth, and Mars, are relatively small rocky worlds with thin atmospheres, while the outer planets became massive giants. Beyond the frost line, The available building materials suddenly included not just rock and metal but abundant water ice, allowing the outer planets to grow much larger and capture thick atmospheres of hydrogen and helium. This single temperature boundary fundamentally shaped the architecture of our solar system. Within the forming planets themselves, another sorting process was taking place called differentiation. As planetesimals grew larger and their interiors heated up from the energy of impacts and the decay of radioactive elements, the materials inside began to melt and separate according to density. Heavy metals, primarily iron and nickel, sank slowly through the molten rock toward the center, forming dense metallic cores. Meanwhile, lighter silicate minerals, rich in silicon and oxygen, rose toward the surface, eventually solidifying into rocky mantles and crusts. This is why Earth today has an iron core surrounded by a rocky mantle, a layered structure that generates our magnetic field and shapes the geology of our planet's surface. This same process occurred in most of the larger bodies of the early solar system, creating the internal structures we detect today through gravity measurements and seismic studies. The growth of planets didn't happen uniformly throughout the disk. Evidence suggests that in the early protoplanetary disk, there was a gap carved out by young Jupiter, whose powerful gravity swept a lane clear of material in its orbital region. This gravitational clearing had profound effects on the inner solar system, limiting the amount of material available to build the terrestrial planets and altering their final compositions. The presence of Jupiter in the outer disk acted like a barrier, preventing material from the outer regions from migrating inward and keeping the inner planets relatively small and metal-rich. Without Jupiter's influence, Earth might have grown much larger, or the distribution of rocky and icy materials throughout the inner system might have been entirely different. Jupiter's role in shaping the solar system may have been even more dramatic than simply carving a gap. The Grand Tack model, named after the sailing maneuver of changing direction, suggests that Jupiter didn't always orbit where it does today. According to this model, as Jupiter grew massive enough to interact strongly with the gas disk, it began migrating inward toward the Sun, perhaps reaching as close as 3.5 astronomical units, roughly where the asteroid belt is today. This inward migration would have scattered rocky material and prevented a large planet from forming in the asteroid belt region. But Jupiter didn't continue inward. When Saturn grew large enough and reached a particular orbital relationship with Jupiter, the two giant planets' combined gravitational influence reversed Jupiter's migration, causing both planets to move back outward to approximately their current positions. This cosmic dance reshaped the distribution of material throughout the inner solar system. The outer solar system also experienced dramatic rearrangements long after the planets formed. The Nice model, named after the French city where it was developed, proposes that the giant planets originally formed in a more compact configuration than we see today, and that they migrated outward over hundreds of millions of years. This migration wasn't smooth and steady, but eventually led to a period of instability when Jupiter and Saturn crossed a critical orbital relationship called a 1:2 resonance, meaning Saturn completed exactly one orbit for every two of Jupiter's. This resonance amplified gravitational interactions between the planets, leading to a dramatic reshaping of the outer solar system. Uranus and Neptune were scattered outward to their current distant orbits, while countless icy planetesimals were flung in all directions. This orbital instability had consequences that rippled throughout the entire solar system. As Uranus and Neptune moved outward, they plowed into the primordial disk of icy bodies beyond Neptune's orbit, scattering these objects throughout the system. Many were ejected into interstellar space, some were captured into unusual orbits that we still observe today, and countless others were sent careening into the inner solar system. This event, occurring roughly 600 million years after the solar system's formation, triggered what we call the Late Heavy Bombardment, a period when the inner planets, including Earth and the Moon, were pelted by an intense barrage of impacts. The scars of this bombardment are still visible in the heavily cratered surfaces of the Moon and Mercury, preserved in regions where geological activity hasn't erased them. This reshuffling of the giant planets may have delayed the emergence of life on Earth or even delivered water and organic materials that made life possible. While the giant planets were settling into their orbits, closer to the Sun, another dramatic event was unfolding that would fundamentally shape our own world. A neighboring protoplanet named Theia, roughly the size of Mars, had formed in an unstable orbit that eventually brought it into collision with the young Earth. This wasn't a head-on collision, but rather a glancing blow that occurred about 4.5 billion years ago, when Earth was still young and partially molten. The impact was catastrophic beyond imagination, vaporizing much of Theia and blasting enormous amounts of material from Earth's outer layers into orbit. The cores of both bodies merged, adding to Earth's iron core, while the debris ejected into orbit quickly coalesced under its own gravity to form the Moon. This giant impact explains many puzzling features of the Earth-Moon system. Why the Moon is unusually large compared to Earth, why it has a small iron core, why its composition closely matches Earth's mantle, and why it's slowly spiraling away from us even today. The Moon we see each night is the child of a violent collision, born from the debris of a world that no longer exists, a reminder that even destructive events can create something beautiful and enduring in the cosmos. The solar system is held together by an invisible force that reaches across vast distances, binding everything within it to the Sun at its center. Gravity, that fundamental force that pulls all matter toward all other matter, creates a hierarchy of orbits and relationships throughout our cosmic neighborhood. The Sun, containing 99.8% of all the mass in the solar system, exerts a gravitational pull so strong that it controls the motion of objects billions of miles away. Everything from the smallest grain of dust to the largest planet moves according to the Sun's gravitational influence, creating a system that has remained stable for billions of years. This gravitational architecture defines the solar system, establishing the boundaries of the Sun's domain and determining which objects remain bound to it and which escape into the darkness of interstellar space. Within this gravitationally bound system exists a remarkable diversity of objects, each with its own story and characteristics. The 8 planets are perhaps the most familiar members of this celestial family, but they represent only a fraction of the solar system's population. Beyond the planets orbit 5 officially recognized dwarf planets, including Pluto in the distant Kuiper belt and Ceres in the asteroid belt, with many more candidates awaiting classification. Hundreds of moons circle the planets and dwarf planets, ranging from tiny irregular captured asteroids to worlds larger than Mercury. The asteroid belt between Mars and Jupiter contains millions of rocky bodies, while countless comets made of ice and dust inhabit the outer reaches of the system. Smaller bodies beyond counting, from boulder-sized rocks to microscopic dust grains, fill the space between worlds, creating a complex ecosystem of objects all moving in their eternal dance around the Sun. One of the most striking features of the solar system becomes apparent when you view it from above or below. All 8 planets orbit the Sun in nearly the same flat plane, like marbles rolling around a slightly tilted dinner plate. This plane, called the ecliptic, is defined by Earth's orbital path, and the other planets deviate from it by only a few degrees. Mercury has the most inclined orbit at about 7 degrees, while most others stay within 3 degrees of the ecliptic plane. This flatness isn't a coincidence but rather a fossil record of the solar system's birth, preserving the geometry of that original rotating disk of gas and dust from which everything formed. The disk's flatness was established by the rotation of the collapsing cloud, and as planets formed within it, they naturally inherited its planar structure. Even today, 4.5 billion years later, this ancient flatness persists, a visible reminder of our origins. The orbits of our 8 planets are also remarkably circular and orderly, especially when compared to the wild variety of planetary systems discovered around other stars. Some exoplanet systems feature giant planets in extremely elongated elliptical orbits or planets whose orbits cross each other's paths, configurations that seem chaotic compared to our own. In our solar system, planetary orbits are nearly circular, with Venus having the most circular orbit of any planet, deviating from a perfect circle by less than 1%. The planets are also well spaced, each occupying its own stable zone without threatening to disturb its neighbors. This orderliness contributes to the long-term stability of the system, allowing planets to orbit for billions of years without dramatic changes. Our solar system's calm, organized structure may be part of what made life on Earth possible, providing a stable environment over the vast timescales needed for evolution to unfold. Another relic of the solar system's formation appears in the direction that objects move. Most objects orbit the Sun in the same direction, a counterclockwise motion when viewed from above Earth's North Pole. This direction is called prograde motion, and it's shared by all 8 planets, most moons, and the majority of asteroids and comets that originate from within the system. Even more remarkably, most planets and moons rotate on their axes in this same direction. This nearly universal motion in one direction traces back to the rotation of that original gas and dust cloud, which spun in a particular direction as it collapsed. The material that formed the Sun and planets inherited this rotation, preserving it across billions of years. The few exceptions, like Venus rotating backward or Uranus rolling on its side, are thought to be the results of catastrophic collisions that altered these worlds after they formed, disrupting the otherwise universal pattern. The solar system itself isn't stationary but races through space as part of something much larger. Our entire solar system orbits around the center of the Milky Way galaxy at approximately 515,000 kilometers per hour, a velocity so immense it's difficult to comprehend. Yet we feel no motion because everything around us, including Earth and the Sun, moves together. We are located about 26,000 light-years from the galactic center, in a minor spiral arm called the Orion Arm or Orion Spur. As we orbit, we carry with us all the planets, asteroids, comets, and everything else bound to the Sun, creating a vast spiral path through the galaxy. This motion has continued since the Sun formed, and it will continue for billions of years into the future, as our solar system slowly circles the galactic heart. One complete orbit around the Milky Way takes approximately 230 million years, a span of time so vast that it's been given its own name, a galactic year or cosmic year. Since the solar system formed 4.6 billion years ago, we've completed roughly 20 galactic orbits, circling the galaxy again and again as the planets orbited the Sun billions upon billions of times. The last time the solar system was in our current position in the galaxy, dinosaurs ruled the Earth during the Triassic period, before the first giant sauropods evolved. One galactic year before that, the supercontinent Pangaea hadn't yet formed, and primitive reptiles were just beginning to dominate the land. These immense timescales remind us that our solar system is part of a larger cosmic ecosystem, one that operates on rhythms far beyond human perception. The inner region of the solar system, The space within the asteroid belt is home to 4 rocky worlds known as the terrestrial planets. Mercury, Venus, Earth, and Mars are fundamentally different from the outer planets, built primarily from rock and metal with thin atmospheres or no atmospheres at all. These are worlds with solid surfaces you could stand on, if you could survive their extreme conditions. Mercury, closest to the Sun, bakes in intense heat on its sunlit side while its dark side plunges to frigid cold. Venus, nearly Earth's twin in size, hides beneath thick clouds of sulfuric acid in an atmosphere so dense it would crush an unprotected visitor. Earth, our home, is the only world we know that harbors life, with its liquid water oceans and oxygen-rich atmosphere. Mars, the outermost terrestrial planet, is a cold desert world with a thin atmosphere, bearing the scars of ancient rivers and lakes that vanished billions of years ago. These 4 worlds share a common architecture but have evolved along dramatically different paths. Beyond the asteroid belt lies the realm of the giant planets, for worlds so different from the terrestrial planets that they seem to belong to an entirely different class of objects. Jupiter and Saturn are known as gas giants, massive worlds composed primarily of hydrogen and helium, the same materials that make up stars, though not dense or hot enough to ignite nuclear fusion. These planets may have small rocky cores buried deep within, but most of their enormous bulk consists of gas compressed to liquid states by the crushing weight of their atmospheres. Uranus and Neptune, the ice giants, are somewhat different in composition, with substantial amounts of water, methane, and ammonia mixed with their hydrogen and helium, materials that were ice in the cold outer regions where they formed. These 4 giants dwarf the terrestrial planets, with Jupiter alone being more massive than all the other planets combined. They're worlds without solid surfaces, where you would simply sink deeper and deeper into increasingly dense atmospheres until pressure crushed any vessel long before reaching whatever core might lie at the center. Jupiter and Saturn together dominate the mass inventory of the solar system outside the Sun itself. Of all the material not contained in the Sun, these 2 giants account for nearly 90%, leaving only a small fraction to be divided among the 6 other planets, all the moons, asteroids, comets, and every other object in the system. Jupiter alone is more than twice as massive as all the other planets combined, a titan that has shaped the evolution of the solar system through its powerful gravitational influence. Saturn, with its spectacular ring system, is the 2nd largest planet, less massive than Jupiter but still enormous by any other standard. These 2 worlds have acted as gravitational shepherds throughout the solar system's history, their gravity flinging comets and asteroids, perhaps protecting the inner planets from some impacts while causing others. The dominance of these 2 giants is a defining characteristic of our solar system, making them key players in the story of how our cosmic neighborhood formed and evolved over billions of years. Mercury, the innermost planet, has a peculiar relationship between its day and its year that puzzled astronomers for decades. For every 2 times Mercury completes an orbit around the Sun, it rotates on its axis exactly 3 times, a relationship called a 3-to-2 spin-orbit resonance. This means that Mercury's day, the time from one sunrise to the next, actually takes 2 Mercurian years to complete. This unusual pattern arose from the tidal forces exerted by the Sun on Mercury's slightly elongated shape, gradually slowing and locking its rotation into this stable configuration over billions of years. The result is a world where the Sun appears to move strangely across the sky, sometimes even reversing direction briefly, and where some locations on the surface experience 2 sunrises and 2 sunsets during a single Mercurian day. This resonance makes Mercury's relationship with the Sun unique among the planets, a gravitational dance frozen into a precise mathematical ratio. Venus, Earth's nearest planetary neighbor, spins in the opposite direction from most other planets, a retrograde rotation that makes the Sun rise in the west and set in the east on its cloud-shrouded surface. Even more remarkable than this backward spin is its extraordinary slowness. Venus takes 243 Earth days to complete a single rotation on its axis, making its day longer than its year, which lasts only 225 Earth days. This means that on Venus, a day is longer than a year, a fact that seems to defy intuition. The cause of Venus's retrograde rotation remains debated among scientists, with theories ranging from a massive ancient impact that knocked the planet sideways to gravitational interactions with the Sun and its thick atmosphere that gradually reversed its spin over billions of years. Whatever the cause, Venus now turns with an agonizing slowness, presenting the same face toward the Sun for months at a time. Despite orbiting farther from the Sun than Mercury, Venus holds the distinction of being the hottest planet in the solar system, with surface temperatures averaging around 470 degrees Celsius, hot enough to melt lead. This extreme heat doesn't come from Venus's distance from the Sun, but from a runaway greenhouse effect that has transformed the planet into a hellish world. Venus's atmosphere, 90 times denser than Earth's, is composed almost entirely of carbon dioxide, a potent greenhouse gas that traps heat with extraordinary efficiency. Thick clouds of sulfuric acid reflect much of the incoming sunlight, yet the heat that does reach the surface becomes trapped by the dense atmosphere, unable to radiate back into space. This trapped heat has built up over billions of years, creating surface conditions more extreme than anywhere else in the solar system. The greenhouse effect that warms Earth to comfortable temperatures has, on Venus, spiraled out of control into a cautionary tale of atmospheric physics taken to an extreme. The upper atmosphere of Venus exhibits another strange behavior called superrotation, where winds race around the planet at speeds of up to 350 kilometers per hour, circling the entire globe in just 4 Earth days. This means the atmosphere rotates about 60 times faster than the solid planet beneath it, creating planet-wide wind patterns that dwarf any weather system on Earth. The mechanism driving this superrotation remains one of planetary science's enduring mysteries, though it likely involves the transport of heat from the day side to the night side and complex interactions between atmospheric layers. These high-altitude winds carry Venus's clouds in a perpetual race around the planet, visible in ultraviolet images as distinctive Y-shaped patterns that sweep across the disk. The contrast between the sluggish rotation of the planet itself and the frenetic speed of its upper atmosphere makes Venus a world of extremes in motion as well as temperature. Earth, our home world, possesses a protective shield that has been crucial to the development and preservation of life. This magnetic field, generated deep within the planet by the motion of molten iron in the outer core, extends tens of thousands of kilometers into space, creating an invisible barrier called the magnetosphere. Convection currents in the liquid metal outer core, driven by heat escaping from the even hotter solid inner core, act like a natural dynamo, converting the motion of electrically conducting material into magnetic field lines that emerge from near the poles and loop through space. This magnetic field deflects the solar wind, a constant stream of charged particles flowing from the Sun that would otherwise strip away Earth's atmosphere over geological time. Without this protection, Earth might have lost its oceans and atmosphere as Mars did billions of years ago, leaving behind a cold, dry world incapable of supporting life. The magnetic field also creates the beautiful auroras near the poles, visible reminders of the invisible shield that guards our planet. Mars has a thin atmosphere composed primarily of carbon dioxide, with a surface pressure less than 1% of Earth's, so tenuous that water cannot exist in liquid form on the surface. Yet despite its thinness, this atmosphere drives dynamic weather patterns across the red planet. Massive dust storms can grow to engulf the entire planet, shrouding the surface in a reddish haze that can last for months. These global dust storms occur every few Martian years, lifting billions of tons of fine dust high into the atmosphere where it absorbs sunlight and alters the planet's temperature structure. Even when global storms aren't raging, Mars experiences constant smaller dust storms and towering dust devils that spiral across the plains, some reaching heights of several kilometers. These vortices, similar to Earth's tornadoes but powered by heating from the sun rather than moisture, have been captured by rovers on the surface and orbiters from above, testament to Mars's active though alien meteorology. The surface of Mars bears the scars of ancient volcanic activity on a scale that dwarfs anything on Earth. Olympus Mons, located in the Tharsis region, rises approximately 25 kilometers above the surrounding plains, making it the tallest volcano and the tallest mountain in the entire solar system. This enormous shield volcano covers an area roughly the size of France, with slopes so gentle that if you stood on its flanks, the curve of the mountain would extend beyond the horizon in every direction. The summit features a complex of overlapping calderas 85 kilometers across, formed by repeated collapses as magma chambers emptied beneath. Olympus Mons grew so large because Mars lacks plate tectonics, allowing volcanic hotspots to build up enormous structures over billions of years as lava repeatedly erupted from the same location. The volcano's last eruptions may have occurred only a few million years ago, relatively recent in geological terms, leaving open the possibility that Olympus Mons could erupt again in Mars's distant future. Stretching along the Martian equator lies Valles Marineris, a vast canyon system that spans roughly 4,000 kilometers, nearly the width of the United States. In places, the canyon plunges 7 kilometers deep and spans 200 kilometers wide, creating a geological feature that makes Earth's Grand Canyon seem like a modest crack in comparison. Valles Marineris wasn't carved by flowing water like canyons on Earth, but rather formed through a combination of tectonic processes and erosion. The canyon system likely began as a series of parallel faults that opened as the Tharsis volcanic region bulged upward billions of years ago, stretching and cracking the surrounding crust. Over time, landslides, wind erosion, and possibly water seepage from underground aquifers widened and deepened these initial cracks into the enormous canyon we see today. The canyon walls reveal layer upon layer of Martian history, a geological record stretching back billions of years waiting to be read by future explorers. Mars's northern hemisphere bears evidence of one of the most catastrophic impacts in solar system history. The North Polar Basin, also known as the Borealis Basin, covers roughly 40% of the planet's surface, making it the largest confirmed impact crater in the solar system. This immense depression, 10,000 kilometers across and several kilometers deep, formed early in Mars's history when a body perhaps the size of Pluto or larger slammed into the planet with unimaginable force. The impact excavated enormous volumes of material and may have fundamentally altered Mars's geological evolution, affecting everything from the planet's volcanic activity to its magnetic field. The dichotomy between Mars's smooth northern lowlands and heavily cratered southern highlands, one of the planet's most prominent features, may be the direct result of this ancient collision. The existence of such a massive impact scar suggests that the early solar system was an even more violent place than we typically imagine, where planet-sized collisions could reshape entire worlds. In the year 2025, a new mission launched toward Mars to unlock mysteries of the red planet's interaction with the solar wind. ESCAPADE, which stands for Escape and Plasma Acceleration and Dynamics Explorers, consists of two small spacecraft that will study Mars's magnetosphere and how the solar wind strips away the planet's atmosphere. Unlike Earth with its global magnetic field, Mars lost its planetary magnetic field billions of years ago, leaving the atmosphere vulnerable to erosion by charged particles from the Sun. Over geological time, this process has stripped away much of what was once a thicker atmosphere, transforming Mars from a potentially habitable world with liquid water on its surface to the cold desert we see today. ESCAPADE will orbit Mars in complementary paths, measuring the plasma dynamics and energy transfer processes that continue to erode the atmosphere even now. Understanding how Mars lost its atmosphere may hold clues to the fate of potentially habitable planets throughout the galaxy and help us better appreciate the protective magnetic shield that has allowed Earth to maintain its oceans and air across billions of years. Jupiter is a world of such immense scale that it challenges our ability to comprehend its size. Approximately 1,000 Earths could fit inside Jupiter's volume, and yet this colossal planet is composed mostly of hydrogen and helium, the lightest elements in the universe. With a mass more than twice that of all the other planets combined, Jupiter is so massive that the center of gravity between it and the Sun actually lies outside the Sun's surface, making their relationship more like a binary system than a simple planet orbiting a star. Despite its enormous size, Jupiter spins faster than any other planet in the solar system, completing a rotation in less than 10 hours. This rapid rotation flattens the planet noticeably at the poles and creates the distinctive bands of clouds that stripe its atmosphere, zones of rising gas alternating with belts of sinking material, each flowing at different speeds and creating the turbulent boundaries where storms are born. Within Jupiter's atmosphere churns a storm so vast and enduring that it has become the planet's most recognizable feature. The Great Red Spot, a high-pressure anticyclonic storm, has been raging for at least several centuries, though it may be much older. When astronomers first observed it through telescopes in the 1600s, it was large enough to swallow 3 Earths side by side. Over the decades and centuries of observation, the storm has changed size and intensity, sometimes shrinking and sometimes growing more vibrant in color, but it has never disappeared. In recent years, the Great Red Spot has been shrinking, now spanning about 1.5 times Earth's diameter, though it remains the largest storm in the solar system. The reddish color likely comes from complex organic molecules created by ultraviolet light breaking apart simpler compounds in Jupiter's atmosphere, though the exact chemistry remains uncertain. Winds at the storm's edges reach speeds of over 400 kilometers per hour, whipping around the oval in a rotation that takes about 6 Earth days to complete. Surrounding Jupiter extends a magnetic field of extraordinary power, approximately 20,000 times stronger than Earth's magnetic field. This magnetosphere, generated by convection currents in Jupiter's metallic hydrogen interior, extends millions of kilometers into space, creating the largest structure in the solar system. If you could see Jupiter's magnetosphere from Earth, it would appear several times larger than the full moon in our sky, despite Jupiter's immense distance. This powerful magnetic field traps charged particles from the solar wind and from volcanic eruptions on the moon Io, creating intense radiation belts far more dangerous than Earth's Van Allen belts. The radiation environment near Jupiter is so severe that spacecraft passing through it must be specially hardened to survive, and any future human missions to the Jovian system will need to account for this hazardous environment. The magnetic field also drives spectacular auroras at Jupiter's poles, far more powerful than Earth's northern and southern lights, as particles spiral down magnetic field lines and slam into the upper atmosphere. Among Jupiter's many moons, the 4 large Galilean satellites stand out, and of these, Callisto holds a unique place. This outermost Galilean moon, slightly smaller than Mercury, appears to have remained geologically inactive for billions of years, preserving on its surface one of the oldest and most heavily cratered landscapes in the solar system. Unlike its sibling moons Europa, Ganymede, and Io, which all show signs of internal activity driven by tidal heating from Jupiter's gravity, Callisto orbits far enough away that tidal forces are weak, leaving its interior cold and inert. The moon's surface is dark and ancient, saturated with impact craters that record billions of years of bombardment. Beneath this battered surface likely lies an ocean of liquid water, kept from freezing by residual heat and dissolved salts, yet this ocean has apparently never interacted with the surface in ways that would erase or modify the ancient cratering record. Callisto remains a frozen archive of the early solar system, a world where time seems to have stopped billions of years ago. Saturn, the second largest planet and perhaps the most beautiful object in the solar system with its magnificent ring system, holds an unusual distinction among all the planets. Its average density is lower than any other planet, so low that if you could find an ocean large enough, Saturn would theoretically float on the surface. This low density arises from Saturn's composition, primarily hydrogen and helium with only a small rocky core, similar to Jupiter but even less compressed despite its substantial mass. The planet's rapid rotation, completing a turn every 10.5 hours, causes it to bulge dramatically at the equator, giving Saturn the most oblate shape of any planet. Like Jupiter, Saturn's atmosphere displays banded cloud patterns, though they're more subdued and covered by a haze of ammonia crystals in the upper atmosphere. Beneath these clouds lies a hydrogen atmosphere that gradually transitions from gas to liquid as pressure increases with depth, eventually reaching a layer of liquid metallic hydrogen surrounding a dense core. The rings of Saturn, visible even through small telescopes from Earth, are composed mainly of billions of individual particles of water ice mixed with smaller amounts of rocky material. These particles range in size from tiny grains like sugar crystals to house-sized boulders, all orbiting Saturn in a disk so thin relative to its diameter that if you built a scale model with rings the thickness of paper, the rings would need to stretch several kilometers across. The ice particles are surprisingly pure, giving the rings their bright, reflective appearance. Despite their vast extent, if you gathered all the ring material together, it would form a moon only about 500 kilometers across, a tiny fraction of Saturn's mass. The age of the rings remains debated, with some evidence suggesting they're relatively young, perhaps only a few 100 million years old, possibly the remains of a shattered moon or comet that ventured too close to Saturn and was torn apart by tidal forces. Within Saturn's ring system lies a prominent gap called the Cassini division, a region about 5,000 kilometers wide that appears dark because it contains far fewer particles than the bright rings on either side. This gap isn't completely empty but has a much lower density of material, and its existence is maintained by a gravitational resonance with Saturn's moon Mimas. Particles orbiting in the Cassini division complete exactly 2 orbits for every 1 orbit of Mimas, a 2-to-1 resonance that causes regular gravitational tugs from the moon. These repeated gravitational interactions pump energy into the particles' orbits, either moving them inward or outward, gradually clearing out the gap. This same principle of orbital resonances creates other gaps and waves throughout Saturn's rings, with various moons acting as gravitational shepherds that sculpt and maintain the ring structure. The rings are far more dynamic than they appear, constantly evolving in response to these gravitational influences. One of Saturn's smaller moons, Enceladus, has proven to be one of the most fascinating objects in the entire solar system. This icy world, only about 500 kilometers in diameter, ejects enormous plumes of water vapor and ice particles from fractures near its south pole called tiger stripes. These plumes, first discovered by the Cassini spacecraft, shoot hundreds of kilometers into space, and some of the material escapes Enceladus entirely, feeding Saturn's diffuse E-ring with fresh ice particles. The source of these plumes is a global ocean of liquid water that exists beneath Enceladus's icy crust, kept liquid by tidal heating as Saturn's gravity flexes the Moon's interior. Chemical analysis of the plume material reveals not just water but also organic molecules and the right chemical conditions for life as we know it. Enceladus has become one of the prime targets in the search for life beyond Earth, a tiny moon that harbors an ocean world where life might exist in the dark waters beneath kilometers of ice. Saturn's largest moon, Titan, is unique among all the moons in the solar system for possessing a thick, substantial atmosphere. This nitrogen-rich atmosphere, denser than Earth's at the surface, creates a surface pressure 1.5 times that of sea level on our planet. The atmosphere extends hundreds of kilometers above Titan's surface, layered with hazes of complex organic molecules created when ultraviolet light from the sun breaks apart methane high in the atmosphere. These organic compounds, known as tholins, give Titan's atmosphere its distinctive orange color and rain down onto the surface, creating landscapes of organic dunes and plains. The atmosphere is so thick and the gravity so low that a human could strap on wings and fly through Titan's skies like a bird. Methane plays the role on Titan that water plays on Earth, existing as liquid, solid, and gas, forming clouds that produce methane rain, filling lakes and seas in the polar regions, and evaporating to continue the cycle. Titan is the only world besides Earth where stable liquid exists on the surface, though here it's liquid methane and ethane rather than water. In the year 2025, the James Webb Space Telescope turned its powerful infrared instruments toward Jupiter, capturing detailed images of the planet's auroras that revealed new understanding of the complex dynamics at Jupiter's poles. These observations showed how Jupiter's magnetic field channels particles into the atmosphere, creating auroral displays far more intense than anything seen on Earth. The infrared wavelengths allowed astronomers to peer through Jupiter's clouds and observe the aurora's structure in unprecedented detail, seeing how they vary over time and respond to changes in the solar wind and volcanic activity on Io. The images revealed intricate structure in the auroral curtains and spots, showing how magnetic field lines map the connections between Jupiter and its moons. These observations help scientists understand not just Jupiter but magnetic processes throughout the universe, from other planets to distant stars, showing how magnetic fields shape the behavior of charged particles across cosmic scales. Uranus stands apart from all the other planets in the solar system due to its extraordinary axial tilt of approximately 98 degrees, meaning the planet essentially rotates on its side relative to the plane of its orbit. While Earth's axis tilts by about 23 degrees, giving us our seasons, and other planets have similarly modest tilts, Uranus rolls around the Sun like a barrel, with its poles pointing almost directly toward and away from the Sun during its solstices. This extreme orientation means that each pole experiences 42 years of continuous sunlight followed by 42 years of darkness during Uranus's 84-year orbit around the Sun. The cause of this unusual tilt likely traces back to one or more massive collisions early in the solar system's history, when a Mars-sized or larger body struck Uranus with enough force to knock it onto its side. This impact may have also affected the planet's internal heat flow and magnetic field, contributing to other peculiarities that make Uranus unique among the ice giants. The tilted rotation creates unusual seasonal patterns in the atmosphere, with some regions experiencing extreme temperature variations while others remain more stable, driving weather patterns unlike anywhere else in the solar system. Uranus possesses a system of rings, though far fainter and less spectacular than Saturn's famous bands. These rings, discovered in 1977 when the planet passed in front of a distant star and the rings briefly blocked its light, are narrow and dark, composed of particles that reflect very little light. The rings maintain their narrow shapes through the gravitational influence of shepherd moons, small satellites that orbit just inside and outside the rings. These moons use orbital resonances to confine ring particles, with their gravity preventing the particles from spreading out into broader, more diffuse bands. When a ring particle drifts too far inward or outward, it encounters a resonance with one of the shepherd moons, receiving a gravitational nudge that pushes it back toward the ring's center. This delicate gravitational architecture keeps the ring stable over millions of years, despite the tendency of orbiting particles to gradually spread out. The ring system of Uranus demonstrates how even subtle gravitational interactions can create and maintain structure in space, with tiny moons exerting influence far beyond what their small masses might suggest. Neptune, the most distant of the 8 major planets, spins with remarkable speed despite its great distance from the Sun and its cold, seemingly placid appearance. The planet completes one rotation in approximately 16 hours, faster than any other planet in the solar system when you consider its size. This rapid rotation, combined with Neptune's active atmosphere, creates the fastest winds known on any planet, with storm systems racing around the planet at speeds exceeding 2,000 kilometers per hour. The Great Dark Spot observed by Voyager 2 in 1989, an Earth-sized storm similar to Jupiter's Great Red Spot, demonstrated the violence of Neptune's weather despite receiving 1,600 times less sunlight than Earth. These powerful winds and storms are driven by internal heat, as Neptune radiates about 2.6 times more energy into space than it receives from the Sun, heat left over from the planet's formation or possibly generated by ongoing gravitational compression deep within its interior. The combination of rapid rotation and internal heat makes Neptune's atmosphere one of the most dynamic in the solar system. Neptune's magnetic field exhibits peculiar characteristics that have puzzled scientists since Voyager 2 measured it during its flyby. Unlike Earth's magnetic field, which roughly aligns with the rotation axis and emerges from near the planet center, Neptune's magnetic field is tilted by 4 to 7 degrees relative to its rotation axis and offset from the center by more than half the planet's radius. This unusual geometry means the magnetic field strength varies dramatically as Neptune rotates, creating a wobbling magnetosphere that tumbles through space. Uranus shares this strange magnetic field geometry, suggesting something fundamental about the internal structure of ice giant planets differs from gas giants like Jupiter and Saturn. The tilted, offset field likely originates not from the planet's core but from a layer of electrically conductive fluid, probably a mixture of water, methane, and ammonia under high pressure, located in the outer portions of the planet's interior. This discovery has changed our understanding of how planetary magnetic fields can be generated, showing that the simple dipole model that works for Earth doesn't apply universally throughout the solar system. Neptune's ring system, fainter even than Uranus's rings, contains an unusual feature in the Adam's ring, the outermost of the planet's main rings. Unlike most planetary rings that form complete circles, the Adam's ring contains 3 prominent arcs, brighter concentrations of material that span only portions of the ring rather than extending all the way around. These arcs, named Libet, Egalite, and Fraternite, maintain their positions and shapes through orbital resonances with Galatea, a small inner moon. The resonance prevents the arc material from spreading evenly around the ring, instead concentrating particles in specific locations. This arrangement seemed impossible when first discovered, as basic orbital mechanics suggests particles should spread uniformly around a ring within months or years, yet the arcs have remained stable for decades. The precise balance between the dispersive tendency of particle collisions and the concentrating influence of the resonance creates this unusual structure, another example of how orbital resonances can sculpt and maintain unexpected features in planetary systems. The arcs are slowly evolving, and long-term observations show subtle changes in their brightness and extent, offering astronomers a chance to watch ring dynamics play out in real time. Neptune holds the distinction of being the coldest major planet in the solar system, with atmospheric temperatures averaging just 73 Kelvin, or about -200 degrees Celsius. This extreme cold might seem surprising given that Uranus orbits closer to the Sun, but Neptune's greater distance isn't the only factor determining its temperature. Neptune radiates significant internal heat, actually keeping its upper atmosphere slightly warmer than Uranus's despite receiving less sunlight. The coldest temperatures occur in the upper atmosphere, where methane condenses into ice crystals, creating the clouds that give Neptune its distinctive blue color. The methane absorbs red light while reflecting blue, similar to Uranus, but Neptune's more active atmosphere and slightly different composition give it a deeper, richer blue hue. At the pressures and temperatures found in Neptune's atmosphere, familiar materials behave in alien ways, with methane existing as ice, liquid, and gas at different altitudes, and water remaining liquid under conditions that would instantly vaporize it on Earth. The cold of the outer solar system transforms even common compounds into exotic states that we rarely encounter in our warmer corner of space. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies left over from the solar system's formation, and here resides Pluto, perhaps the most famous dwarf planet. Pluto orbits the Sun in a peculiar elliptical path that takes it inside Neptune's orbit at perihelion, though the two bodies never collide due to a 3-to-2 orbital resonance that keeps them coordinated. For every 2 orbits Pluto completes around the Sun, Neptune completes exactly 3, and this relationship ensures Pluto is always far from Neptune when their paths cross. This resonance stabilizes Pluto's orbit over billions of years, protecting it from being ejected from the solar system or colliding with Neptune. Pluto shares this resonance with hundreds of other Kuiper Belt objects called Plutinos, all locked in the same gravitational relationship with Neptune. The resonance is a relic of Neptune's outward migration early in the solar system's history, when the ice giant's gravity swept up objects and captured many of them into stable resonances as it moved to its current orbit. Pluto's membership in this resonant population helped lead to its reclassification from planet to dwarf planet, as it became clear that Pluto was simply one of many similar objects in the outer solar system. Pluto and its largest moon Charon form a unique binary system unlike any planet-moon pair in the solar system. Charon is so large relative to Pluto, about half Pluto's diameter and 1/8 its mass, that the two bodies orbit around a point that lies in the space between them rather than inside Pluto itself. This center of mass, called the barycenter, lies about 1,500 kilometers above Pluto's surface, making Pluto and Charon more like a double dwarf planet system than a traditional planet and moon. The two bodies are tidally locked, not just with Charon always showing the same face to Pluto, as our moon does to Earth, but with both bodies locked to each other, so each always shows the same face to its partner. They orbit this common point every 6.4 days, spinning synchronously like cosmic dancers forever facing one another. The formation of this binary system likely resulted from a giant impact early in Pluto's history, when another Kuiper Belt object struck Pluto at just the right angle and speed to create Charon from the debris, similar to how our moon formed from the impact between Earth and Theia, though on a smaller scale. In the scattered disk region beyond the main Kuiper belt orbits Haumea, one of the strangest objects in the solar system. This dwarf planet spins once every 4 hours, faster than any other known body larger than 100 kilometers in diameter, and this rapid rotation has deformed Haumea into an elongated ellipsoid shape rather than a sphere. The centrifugal force from the spin stretches the body, making it roughly twice as long as it is wide, resembling an American football tumbling through space. Haumea's surface appears to be covered in crystalline water ice, giving it an unusually high reflectivity that makes it bright despite its small size and great distance. In 2017, astronomers discovered that Haumea possesses a ring, making it the first Kuiper belt object known to have such a feature. The ring orbits Haumea's equator in the same plane as the dwarf planet's rotation, likely formed from debris created by an ancient impact. Haumea also has 2 known moons, Hyakka and Namaka, which may be fragments from the same collision that created the ring. The entire Haumea system, with its rapid rotation, elongated shape, ring, and moons, tells a story of a violent past collision that shattered and reshaped this distant world. The discovery of Eris in 2005 ultimately triggered the most significant reclassification in the solar system since the planets were first recognized as distinct from stars. Eris orbits in the scattered disk, a region beyond the Kuiper belt containing objects with highly elliptical orbits, and its discovery revealed it to be slightly larger than Pluto with a significantly greater mass. This posed a problem for astronomers, as Eris clearly seemed to qualify as a planet by the same criteria that had made Pluto one, yet accepting Eris as the 10th planet would mean accepting potentially dozens more as additional Kuiper belt objects were discovered. The astronomical community faced a choice: either expand the number of planets to include all large Kuiper belt objects, or create a new classification that would distinguish the 8 classical planets from these smaller outer solar system bodies. In 2006, the International Astronomical Union voted to create the dwarf planet category, requiring that a planet must have cleared its orbital neighborhood of other debris, something the 8 major planets have accomplished but Pluto and Eris have not. The decision reclassified Pluto, ending its 76-year reign as the 9th planet and acknowledging that the outer solar system contains an entire population of large icy bodies, each interesting and worthy of study, but fundamentally different from the 8 dominant worlds that truly govern the architecture of the solar system. Deep within the main asteroid belt, between the orbits of Mars and Jupiter, lies Ceres, the only dwarf planet residing in the inner solar system. Despite being surrounded by millions of asteroids, Ceres is so massive that it contains approximately 1/3 of the total mass of the entire asteroid belt, a remarkable dominance that sets it apart from all its neighbors. With a diameter of about 940 kilometers, Ceres is large enough that its own gravity has pulled it into a nearly spherical shape, unlike the irregular potato-shaped forms of smaller asteroids. When the Dawn spacecraft arrived at Ceres in 2015, it revealed a world far more complex than expected, with a surface marked by impact craters, mysterious bright spots of exposed salts, and evidence of recent geological activity. The bright spots, particularly prominent in Orcata crater, appear to be deposits of sodium carbonate and other salts left behind by briny water that seeped up from below and evaporated on the surface. These features suggest that Ceres is not simply a dead rock but a world that has experienced internal activity within relatively recent geological time, possibly continuing even today. Beneath Ceres's rocky, cratered surface may lie a global ocean of liquid water, making this dwarf planet a potential ocean world hidden in plain sight within the asteroid belt. Evidence from the Dawn mission suggests that a layer of briny water or water-saturated mud exists beneath the crust, kept from freezing by salts dissolved in the water and possibly by residual heat from radioactive decay in Ceres's rocky interior. The presence of ammonia-bearing minerals on the surface hints that Ceres may have formed farther out in the solar system, beyond the frost line where ammonia ice was common, and later migrated inward to its current position. If Ceres does harbor a subsurface ocean, it would join a growing list of ocean worlds in the solar system that includes Jupiter's moon Europa, Saturn's moon Enceladus, and possibly several other large moons. The prospect of liquid water existing for billions of years within Ceres raises intriguing questions about whether simple life could have emerged in this isolated environment, cut off from sunlight but potentially rich in dissolved minerals and chemical energy. The asteroid belt is not uniformly populated but contains distinct gaps where few asteroids orbit, regions called Kirkwood gaps after the astronomer who first explained them. These gaps appear at specific distances from the Sun where an asteroid's orbital period would be a simple fraction of Jupiter's orbital period, creating orbital resonances similar to those that shape planetary rings. An asteroid orbiting in a 3-to-1 Kirkwood gap, for example, would complete exactly 3 orbits for every 1 orbit of Jupiter, receiving regular gravitational tugs from the giant planet at the same point in its orbit. Over millions of years, these repeated gravitational interactions pump energy into the asteroid's orbit, increasing its eccentricity until the orbit becomes unstable and the asteroid is perturbed into a different path. The result is gaps in the asteroid belt at specific distances corresponding to these resonances, empty lanes carved by Jupiter's gravitational influence. Other resonances don't create gaps but instead concentrate asteroids, showing how the same physical mechanism can either clear or populate orbital regions depending on the specific mathematical relationship involved. Jupiter's gravitational influence extends far beyond creating gaps in the asteroid belt. The planet's gravity creates stable points in space called Lagrange points, locations where the gravitational pull of Jupiter and the Sun balance in such a way that objects can remain relatively stationary. 2 of these points, designated L4 and L5, sit 60 degrees ahead of and behind Jupiter in its orbit, forming equilateral triangles with Jupiter and the Sun. These locations are stable, meaning that objects placed there tend to stay there, oscillating gently around the equilibrium point rather than drifting away. Over billions of years, these Lagrange points have collected large populations of asteroids called Trojan asteroids, with the leading swarm at L4 called the Greek camp and the trailing swarm at L5 called the Trojan camp, names derived from the Homeric epics. Jupiter's Trojans number in the thousands, possibly millions if you count smaller bodies, making them a substantial population rivaling the main asteroid belt. Other planets also have Trojan asteroids at their Lagrange points, but Jupiter's are by far the most numerous, another testament to the giant planet's gravitational dominance of the solar system. Among the larger asteroids in the main belt, Vesta stands out as a particularly intriguing world, a body that began differentiating into layers like a planet before its growth was interrupted. The Dawn spacecraft's detailed study of Vesta revealed the Rear Sylvia crater, an enormous impact basin that dominates the asteroid's southern hemisphere. This impact, which occurred perhaps 1 billion years ago, excavated material from deep within Vesta's interior and created a central peak that rises approximately 22 kilometers above the crater floor, making it one of the tallest mountains in the entire solar system, nearly 3 times the height of Mount Everest. The impact was so powerful that it ejected substantial amounts of debris into space, material that has since spread throughout the inner solar system. Some of this debris has fallen to Earth as a particular class of meteorites called HED meteorites, basaltic achondrites, eucrites, and diogenites that bear the chemical signatures of Vesta's differentiated interior. By studying these meteorites in laboratories and comparing them with Dawn's observations of Vesta's surface, scientists can piece together the asteroid's internal structure and thermal history, using Vesta as a window into the processes that built the rocky planets during the solar system's youth. The Alinda family of asteroids represents a population of bodies whose orbits have been shaped by close encounters with Jupiter's gravitational influence. These asteroids orbit in the inner solar system but have orbital periods that place them near resonances with Jupiter, particularly the 3:1 and 1:1 resonances. Rather than being ejected by these resonances like asteroids in the Kirkwood gaps, Alinda family members have their orbital eccentricities increased, stretching their orbits into more elongated ellipses that can cross the paths of the inner planets. This makes some Alinda asteroids potentially hazardous to Earth, as their eccentric orbits can bring them into the inner solar system where close approaches to terrestrial planets become possible. The interaction with Jupiter's resonances gradually pumps up the eccentricity over millions of years, demonstrating how Jupiter continues to reshape the asteroid belt even billions of years after the solar system formed. The Alinda family shows that the asteroid belt is not a static collection of rocks but a dynamic population constantly being stirred by the gravitational influences of the giant planets. Comets, those spectacular visitors from the outer solar system that grow glowing tails as they approach the Sun, come from two distinct reservoirs with very different characteristics. Short-period comets, those with orbital periods less than 200 years, originate primarily from the Kuiper belt, the region beyond Neptune where Pluto and thousands of other icy bodies orbit. These comets travel in relatively circular orbits close to the plane of the solar system, and their periods are measured in years or decades rather than centuries or millennia. When gravitational perturbations from Neptune or encounters with other Kuiper belt objects nudge these icy bodies onto orbits that carry them into the inner solar system, they become active comets, their ices sublimating in the Sun's heat to create the distinctive coma and tail. Halley's Comet, perhaps the most famous comet of all, is a short-period comet that returns to the inner solar system every 76 years, its orbit taking it from just inside Earth's orbit out beyond Neptune's. The relatively frequent returns of short-period comets make them easier to study and track, and some have been visited by spacecraft that revealed their ancient, pristine surfaces. Long-period comets follow a different path into the inner solar system, arriving from the Oort cloud, a vast spherical shell of icy bodies that surrounds the solar system at distances of tens of thousands of astronomical units from the Sun. The Oort cloud, proposed by Dutch astronomer Jan Oort in 1950 to explain the orbits of long-period comets, has never been directly observed because its members are too small and too distant to detect until they fall inward toward the Sun. These comets can have orbital periods of thousands, millions, or even billions of years, and they approach the inner solar system from all directions rather than staying near the ecliptic plane like short-period comets. A passing star or the gentle gravitational tide of the Milky Way itself can nudge an Oort cloud object onto a trajectory that sends it plunging toward the Sun, beginning a journey that may take millions of years. When these comets finally arrive in the inner solar system, they often put on spectacular shows with their bright comae and long tails, as they're seeing sunlight for the first time in their existence and releasing volatiles that have been frozen since the solar system's formation. Many long-period comets visit the inner solar system only once before being ejected entirely or having their orbits altered into short-period paths by gravitational encounters with the giant planets. Jupiter plays a crucial role in determining the ultimate fate of comets that venture into the inner solar system. When a comet's orbit brings it close to Jupiter, the giant planet's immense gravity can radically alter the comet's path. Some comets are captured into shorter period orbits, becoming Jupiter family comets that return regularly. Others have their orbits stretched, sending them back to the outer solar system or the Oort cloud on extremely elongated paths. But many comets receive enough energy from a Jupiter encounter to be ejected from the solar system entirely, flung outward with velocities exceeding the Sun's escape velocity. These comets become interstellar wanderers, drifting through the galaxy for billions of years until perhaps encountering another star system. Jupiter acts as a gravitational gatekeeper, ejecting a significant fraction of the comets that pass near it and thereby limiting the population of comets that can threaten the inner planets with impacts. This protective role has been important throughout Earth's history, as Jupiter's gravity has likely reduced the frequency of cometary impacts that might have disrupted the development of life on our world. Jupiter's influence extends beyond just comets to the broader population of small bodies scattered throughout the solar system. Objects in the scattered disk, a region beyond the Kuiper belt containing bodies on highly eccentric and inclined orbits, frequently have close encounters with Neptune, which in turn can send them into orbits that eventually bring them near Jupiter. Studies of the long-term dynamics of these populations suggest that Jupiter ejects approximately 90% of scattered disk objects from the solar system over billions of years, an astonishing efficiency that demonstrates the giant planet's dominance over the architecture of the outer solar system. This ejection process has been ongoing since the solar system's formation, meaning the current population of scattered disk objects and comets represents only a small fraction of what once existed. Billions upon billions of icy bodies have been flung into interstellar space by Jupiter's gravity, carrying with them material from our solar system's formation and seeding the galaxy with samples of the Sun's planetary disk. Some of these ejected bodies may eventually encounter other stellar systems, becoming captured by new stars or simply passing through as visitors from a distant solar system, continuing their journeys through the cosmos for eons to come. The Kuiper belt stretches across a vast region of the outer solar system, beginning at approximately 30 astronomical units from the Sun, just beyond Neptune's orbit, and extending outward to roughly 50 astronomical units. This distant realm remains cold and dark, receiving only a tiny fraction of the sunlight that warms the inner planets, and here the temperatures hover just a few dozen degrees above absolute zero. The Kuiper belt is a flattened disk of material that roughly follows the plane of the planetary orbits, though many of its members travel on paths that are somewhat tilted or elongated compared to the nearly circular orbits of the major planets. This region represents a fossil record of the early solar system, preserving icy planetesimals that never coalesced into a major planet, their growth arrested when Neptune's formation and subsequent migration stirred the region and scattered most of the material that once existed there. What remains today is perhaps only a small percentage of the original population, the survivors of billions of years of gravitational interactions, collisions, and ejections that have shaped this distant frontier. Within the Kuiper belt orbit billions of icy bodies, most too small and distant to observe directly with current telescopes, but their collective presence reveals itself through the handful of larger objects we can detect and study. These bodies are remnants of the solar nebula, the original disk of gas and dust from which the planets formed, composed primarily of water ice, methane ice, ammonia ice, and rocky materials. Unlike the asteroids of the inner solar system, which are mostly rock and metal because they formed inside the frost line, Kuiper belt objects condensed in the cold outer regions where volatile ices could remain solid. This icy composition makes them more like the building blocks of the giant planets' cores than like the terrestrial planets. Some Kuiper belt objects are quite large, with Pluto being the most famous example, but the vast majority are small bodies ranging from a few kilometers to a few hundred kilometers across. Every so often, Collisions between these objects create families of fragments sharing similar orbits, and occasionally one gets knocked onto a trajectory that sends it into the inner solar system, where we observe it as a comet. The classical Kuiper belt objects, sometimes called Cubewanos after the first discovered member designated 1992 QB1, orbit in relatively stable, near-circular paths that have remained largely undisturbed since the solar system's formation. These objects avoided the gravitational chaos that scattered many of their neighbors, residing in a zone where Neptune's influence is present but not overwhelming. Their orbits are dynamically cold, meaning they have low eccentricities and inclinations, traveling around the Sun in orderly paths that have persisted for billions of years. Classical Kuiper belt objects represent the most pristine remnants of the protoplanetary disk's outer regions, having experienced minimal heating, alteration, or disturbance since they formed. Studying these objects provides astronomers with insights into the conditions and processes that existed in the early solar system, a window into an era when the planets were still forming and the Sun was a young star surrounded by a disk of primordial material. The surfaces of classical Kuiper belt objects often display red colors, possibly from organic compounds created by billions of years of irradiation by cosmic rays and ultraviolet light, a slow cooking process that gradually alters their surface chemistry. Beyond and overlapping with the classical Kuiper belt lies the scattered disk, a region populated by objects on highly eccentric and inclined orbits that bear the unmistakable signatures of gravitational interactions with Neptune. Scattered disk objects travel on elongated elliptical paths that can carry them from perihelion distances of 30 or 40 astronomical units out to aphelion distances of 100 astronomical units or more, vast ellipses that take hundreds or thousands of years to complete. These objects were likely once members of the Kuiper belt proper but were scattered onto their current orbits by close encounters with Neptune, particularly during the period when Neptune was migrating outward to its present orbit. Each time a scattered disk object returns to the inner part of its orbit, there's a chance it will experience another encounter with Neptune, which might eject it from the solar system entirely, send it deeper into the scattered disk, or even capture it into a more circular orbit. The scattered disk is therefore a transient population, constantly being refilled by new objects kicked out of the Kuiper belt while losing members to ejection and capture, a dynamic region that connects the classical Kuiper belt to the even more distant Oort cloud. Far beyond the Kuiper belt and scattered disk, at distances so vast that the Sun appears merely as the brightest star in the sky, lies the hypothetical Oort cloud, a vast spherical shell of icy bodies that may extend outward to 100,000 astronomical units or more, nearly halfway to the nearest star. The Oort cloud has never been directly observed because its members are too small and too far away to detect with current telescopes, but its existence is inferred from the orbits of long-period comets that arrive from all directions rather than from the plane of the solar system. These comets must originate from a spherical distribution of source objects surrounding the Sun, and the Oort cloud provides the only explanation that fits the observations. The cloud may contain trillions of icy bodies, the remnants of planetesimals that formed in the region of the giant planets but were ejected outward by gravitational encounters during the solar system's youth. These objects were flung to such great distances that the Sun's gravity barely holds them, and they orbit with periods measured in millions of years, moving so slowly through space that their positions remain almost fixed over human timescales. The Oort cloud is thought to have structure, with an inner region sometimes called the Hills cloud after the astronomer who proposed it. This inner Oort cloud occupies the region between approximately 2,000 and 20,000 astronomical units from the Sun, much closer than the outer Oort cloud but still incredibly distant on human scales. The Hills cloud may be more of a torus or thick disk than a sphere, retaining some memory of the original disk-like structure of the protoplanetary disk, while the outer Oort cloud forms a more uniform spherical shell. Objects in the inner Oort cloud are more tightly bound to the Sun than those in the outer reaches, and therefore less susceptible to being stripped away by passing stars or the general gravitational environment of the galaxy. The boundary between the scattered disk and the inner Oort cloud remains somewhat arbitrary and poorly defined, as we haven't observed objects in this transitional region directly, but dynamical models suggest it's a vast reservoir of icy bodies waiting to be discovered when future telescopes gain the sensitivity to detect them. The Oort cloud's great distance from the Sun makes its members vulnerable to external gravitational influences that are negligible in the inner solar system. Passing stars, which occasionally come within a light year or two of the Sun during their random motions through the galaxy, can gravitationally perturb Oort cloud objects, slightly altering their orbits. Even more subtle is the galactic tide, the gradient in gravitational pull across the Oort cloud caused by the combined mass of all the stars and dark matter in the Milky Way. This galactic tide varies as the Sun orbits the galactic center, sometimes strengthening and sometimes weakening as we pass through regions of different stellar density. Both passing stars and galactic tides can nudge Oort cloud objects onto new orbits, and occasionally these nudges send objects falling inward toward the Sun. The perturbed objects begin a long journey inward, accelerating as the Sun's gravity grows stronger, eventually plunging through the planetary system where they become visible as long-period comets. This process occurs continuously but randomly, with the rate depending on the density of nearby stars and the phase of the Sun's galactic orbit. These disturbances to the Oort cloud send comets cascading into the inner solar system on timescales of millions of years, creating a steady rain of icy visitors that has continued throughout the solar system's history. On average, a new long-period comet bright enough to observe appears every few years, but the actual rate of objects entering the inner solar system is much higher when you count smaller bodies that never grow bright enough to detect from Earth. Statistical studies of comet orbits suggest that major disturbances to the Oort cloud occur roughly every few million years, perhaps when the Sun passes particularly close to another star or travels through a dense region of the galactic disk. These events may trigger comet showers, periods when the flux of comets entering the inner solar system increases significantly, potentially affecting impact rates on Earth and the other planets. Some researchers have speculated that past mass extinction events on Earth might correlate with comet showers triggered by Oort cloud disturbances, though the evidence remains controversial. What's certain is that the Oort cloud continues to supply the inner solar system with fresh cometary material billions of years after the planets formed, a legacy of the solar system's violent youth preserved in the deep freeze of the outer limits of the Sun's gravitational domain. The Sun's gravitational influence extends remarkably far into space, creating a region called the Hill sphere or Roche sphere where the Sun's gravity dominates over the gravitational pull of other stars and the galaxy as a whole. This sphere extends approximately 3.8 light-years from the Sun, though the boundary is fuzzy and depends on the direction you measure because the Sun is moving through the galaxy and tidal forces distort the sphere into an elongated shape. Within the Hill sphere, objects orbit the Sun rather than escaping into interstellar space or being captured by other stars, though the Sun's hold on objects in the outer Oort cloud is tenuous. The vast extent of the Hill sphere means that the solar system's true boundary lies far beyond the visible planets, encompassing a volume of space thousands of times larger than the region containing the 8 major planets. This distant frontier represents the edge of the Sun's domain, beyond which lies the interstellar medium, the sparse gas and dust that fills the space between stars, and the gravitational influences of neighboring stellar systems. In recent years, astronomers have detected 3 confirmed interstellar objects passing through the solar system, visitors from other stellar systems that have entered the Sun's sphere on hyperbolic trajectories that will carry them back out into interstellar space. The first, Oumuamua, was discovered in 2017 and caused immense excitement and some controversy due to its unusual elongated shape and slight non-gravitational acceleration that remains not fully explained. The second, Comet Borisov, arrived in 2019 and appeared more comet-like, with a visible tail and composition similar to comets from our own Oort cloud, suggesting that comet formation processes might be similar across different stellar systems. The third visitor, designated Atlas, has more recently been identified as following a hyperbolic orbit, another traveler from the space between stars. These interstellar visitors provide the first direct samples of material from other planetary systems, offering glimpses of how planets and small bodies form around other stars. Statistical calculations suggest that interstellar objects might pass through the inner solar system fairly regularly, perhaps several per year, but most go undetected because they're small and faint, and we're only now developing the survey capabilities to spot them. As our telescopes improve and survey programs expand, we'll likely discover many more of these cosmic wanderers, each carrying information about its home system and the diversity of planetary formation throughout the galaxy, silent messengers from distant suns that briefly visit our solar neighborhood before continuing their endless journeys through the vast spaces between the stars. Magnetic fields represent one of the most varied characteristics across the solar system, with each world generating or failing to generate magnetic fields through different mechanisms and displaying vastly different field strengths and geometries. The magnetic fields of planets arise from the motion of electrically conductive fluids in their interiors, a process called a dynamo, but the nature of these fluids and the resulting fields varies tremendously. Earth and the gas giants Jupiter and Saturn have strong magnetic fields generated in layers of liquid metal, with Jupiter's field being by far the most powerful. Mercury has a weak but detectable field despite its small size, suggesting a partially molten core. Venus and Mars lack significant global magnetic fields today, though Mars once had a strong field that died billions of years ago when its core cooled. The moons of the solar system mostly lack intrinsic magnetic fields, with Jupiter's moon Ganymede being the notable exception, possessing a small magnetosphere of its own nested within Jupiter's enormous magnetic environment. Even within the categories of rocky planets, gas giants, and ice giants, the magnetic field characteristics diverge in surprising ways that reveal fundamental differences in internal structure and dynamics. Saturn's magnetic field displays an unusual characteristic that puzzled scientists for decades. Its field axis aligns almost perfectly with the planet's rotation axis, with a tilt of less than 1 degree between the magnetic and rotational poles. This near-perfect alignment seems too precise to be coincidental and suggests something unusual about Saturn's internal structure or dynamo mechanism. Recent research proposes that the alignment results from helium rain falling through Saturn's interior, a process unique to this planet. Deep within Saturn, where pressures reach millions of times Earth's atmospheric pressure and temperatures soar to thousands of degrees, helium becomes insoluble in the surrounding metallic hydrogen and begins to condense into droplets. These droplets, denser than the hydrogen around them, rain downward toward the core, releasing gravitational potential energy that converts to heat. This helium rain may create a stable layer in Saturn's interior that suppresses asymmetries in the dynamo, forcing the magnetic field to align with the rotation axis. The process also helps explain why Saturn radiates more heat than it receives from the Sun, as the falling helium releases energy that gradually works its way to the surface and radiates into space, a gentle rain that has continued for billions of years, slowly depleting Saturn's atmosphere of helium while shaping its magnetic field into its unusual configuration. Among the moons of the solar system, Mimas, a small satellite of Saturn, possesses the lowest escape velocity of any substantial moon, requiring a speed of only about 160 meters per second to reach freedom. This modest velocity, roughly the speed of a commercial jet aircraft, results from Mimas's small size, just under 400 kilometers in diameter, and its low density, suggesting it's composed primarily of water ice with little rock. An astronaut standing on Mimas could almost jump into orbit with the right equipment, and any material ejected by impacts has a high probability of escaping entirely rather than falling back to the surface. Mimas is famous for its enormous crater Herschel, an impact scar 1/3 the diameter of the Moon itself, with a central peak rising 6 kilometers from the crater floor. The impact that created this crater must have come close to shattering Mimas entirely, and the low escape velocity meant that much of the ejected material was lost to space rather than accumulating back on the surface. The Moon's appearance, with this single dominant crater, has earned it comparisons to the Death Star from science fiction, though Mimas formed billions of years before those films and tells a real story of cosmic violence in the early solar system. The compositional gradients visible across the solar system preserve a record of conditions in the early protoplanetary disk, particularly the temperature structure established by the young sun's heat. Close to the sun, temperatures were high enough that only materials with very high condensation points could remain solid, metals like iron and nickel, and rocky minerals like silicates. Farther out, beyond the frost line at approximately 5 astronomical units, temperatures dropped low enough for water ice to condense, followed by other volatile ices like ammonia and methane at even greater distances. This temperature gradient created a compositional gradient, with the inner planets composed primarily of rock and metal, the outer planets containing vast amounts of ice along with rock and metal in their cores, and the outermost regions rich in the most volatile ices. The gradient remains visible today in the densities and compositions of planets, moons, asteroids, and comets, each reflecting the conditions at the location where it formed. Objects that formed inside the frost line are dense and rocky. Those that formed just beyond it contain abundant water ice mixed with rock, and those from the far outer regions are rich in methane and nitrogen ices, a cosmic archaeology that lets us reconstruct the thermal structure of the early solar system. The terrestrial planets Mercury, Venus, Earth, and Mars all share a general compositional similarity, being composed of silicate rock mantles surrounding iron-nickel metal cores, but their densities vary in ways that reflect their different formation locations and thermal histories. Earth has the highest density of any planet in the solar system, approximately 5,500 kilograms per cubic meter when measured without accounting for gravitational compression, followed closely by Mercury at about 5,400 kilograms per cubic meter. Mars has a lower density around 3,900 kilograms per cubic meter, and Venus falls between Earth and Mars at roughly 5,200 kilograms per cubic meter. Mercury's high density, despite its small size, indicates it has an unusually large iron core relative to its silicate mantle, possibly the result of a giant impact that stripped away much of its original mantle early in its history. Mars's lower density suggests a smaller iron core fraction and possibly incorporation of lighter elements or water in its interior. These density differences encode information about the building blocks that assembled into each planet and the violent collisions that shaped them during their formation, with each world's final density reflecting its unique history. The ice giants Uranus and Neptune, despite their name, don't consist primarily of conventional water ice but rather contain large amounts of materials that were ices in the cold outer solar system where they formed water, ammonia, and methane. In the high-pressure, high-temperature conditions inside these planets, these materials don't exist as ice but rather as hot, dense fluids or exotic states of matter like superionic ice. The term ice giants refers to the composition rather than the physical state, distinguishing these planets from the gas giants Jupiter and Saturn, which are composed mostly of hydrogen and helium. Uranus and Neptune likely have relatively small rocky cores surrounded by thick mantles of these icy materials, topped by atmospheres of hydrogen, helium, and methane. The methane in their atmospheres absorbs red light, giving both planets their distinctive blue colors, though Neptune's deeper, richer blue suggests additional chromophores or different methane concentrations and distributions. The abundance of these heavy elements in ice giants relative to hydrogen and helium places them in a different category from gas giants and has important implications for understanding planetary formation, as these heavy elements may have been easier to accumulate than hydrogen and helium in the outer regions of the protoplanetary disk where Neptune and Uranus formed, before they were possibly scattered to their current positions by gravitational interactions during the solar system's early dynamical evolution. The vastness of space holds within it a profound truth that often goes unspoken in our everyday contemplation of the cosmos. Our solar system, this island of matter orbiting a middle-aged star, is not a museum piece frozen in time. It breathes with motion, changes with the passing of eons, and continues its ancient dance even as we observe it from our small blue world. The ice giants Uranus and Neptune generate their magnetic fields through a fundamentally different process than the terrestrial planets and gas giants. Rather than arising from convection in a metallic core or metallic hydrogen layer, their magnetic fields appear to originate in a thick layer of superionic water, ammonia, and methane that exists under the extreme pressures found in the outer portions of their interiors. In this exotic state of matter, the oxygen atoms from water molecules form a crystalline lattice while hydrogen ions flow freely through the structure, creating an electrically conductive fluid without requiring the extreme pressures needed to metallize hydrogen. This dynamo layer sits relatively close to the surface compared to the deep core dynamos of other planets, explaining why the magnetic fields of Uranus and Neptune are tilted and offset from their centers rather than aligning with their rotation axes and emerging from their cores. The discovery that planetary magnetic fields can be generated in such unusual ways has expanded our understanding of what's possible in planetary interiors and suggests that exoplanets with similar compositions might display equally strange magnetic field geometries. These offset, tilted fields create magnetospheres that wobble dramatically as the planets rotate, presenting different orientations to the solar wind with each spin and creating dynamic environments unlike anything found around other planets. Atmospheric dynamics across the solar system display dramatic differences that reflect each world's size, composition, rotation rate, and distance from the Sun. Earth's atmosphere, driven by solar heating and the planet's rotation, creates familiar weather patterns of high and low pressure systems, jet streams, and storm systems that we experience daily. Venus's thick atmosphere exhibits a phenomenon called superrotation where winds circle the planet far faster than the planet itself rotates, driven by still mysterious mechanisms involving heat transport from day to night side. Mars's thin atmosphere supports dust storms that can grow to engulf the entire planet, lofted by temperature differences and sustained by the dust itself absorbing sunlight. The gas giants display banded cloud structures where zones of rising gas alternate with belts of sinking material, each flowing at different speeds to create the distinctive striped appearance. These bands emerge from the interaction between the planet's rapid rotation, which creates strong Coriolis effects, and convection driven by internal heat rising from the depths. The resulting atmospheric dynamics can maintain stable features like Jupiter's Great Red Spot for centuries, while also producing transient storms that appear and disappear over months or years. Neptune's atmosphere hosts some of the most extreme wind speeds recorded anywhere in the solar system, with storms racing around the planet at velocities exceeding 2,000 kilometers per hour, far faster than the strongest hurricanes on Earth. These tremendous winds seem paradoxical given that Neptune receives less than 1% of the sunlight that reaches Earth, yet somehow generates these violent atmospheric motions. The energy driving Neptune's winds comes primarily from internal heat, as the planet radiates about 2.6 times more energy into space than it absorbs from the Sun. This internal heat, left over from the planet's formation or possibly generated by ongoing gravitational settling of heavier elements toward the core, rises through convection and powers atmospheric circulation. The combination of this heat source, Neptune's rapid 16-hour rotation, and the low friction in the hydrogen-helium atmosphere allows winds to reach extraordinary speeds. Dark spots similar to Jupiter's Great Red Spot appear and disappear in Neptune's atmosphere over periods of years, enormous storm systems that rotate in the opposite direction to the surrounding flow. The Voyager 2 spacecraft captured images of one such storm in 1989, a feature called the Great Dark Spot that spanned an area the size of Earth, though subsequent observations by the Hubble Space Telescope revealed it had vanished by 1994, replaced by new dark spots in different locations, demonstrating the transient nature of even Neptune's largest atmospheric features. Mercury holds the distinction of having the lowest escape velocity of any major planet in the solar system, requiring a speed of only about 4.3 kilometers per second to break free of its gravitational pull. This low escape velocity results from Mercury's small mass, only about 5.5% of Earth's mass, and its compact size, with a radius less than 40% of Earth's radius. The weak gravity has consequences for Mercury's ability to retain an atmosphere. Any gases released by volcanic activity or impacts quickly escape into space unless they're very heavy or very cold. This explains why Mercury has only an extremely tenuous exosphere rather than a proper atmosphere, composed of atoms temporarily captured from the solar wind or knocked off the surface by micrometeorite impacts. These atoms bounce around the surface a few times before gaining enough energy to escape, creating a constantly replenished but never substantial atmosphere. The low escape velocity also means that a future spacecraft could take off from Mercury's surface more easily than from any other planet, requiring far less fuel than a launch from Earth, Moon, or Mars, a factor that might make Mercury an attractive destination for resource extraction if its proximity to the Sun and lack of atmosphere didn't pose such severe challenges. The asteroid belt continues to evolve as collisions grind large bodies into smaller ones, creating the dust that zodiacal light scatters across our night sky. Even the Sun changes, growing slowly brighter as fusion in its core alters its composition, a brightening that will eventually make Earth uninhabitable long before the Sun exhausts its hydrogen fuel. The architecture we observe today, with small rocky planets close to the Sun and giant worlds farther out, with a belt of asteroids and a distant realm of icy bodies, did not emerge fully formed from the primordial disk of gas and dust. Planetary migration, the movement of worlds through the solar system as they exchanged momentum with the disk and with each other, sculpted what we see now. The giant planets likely formed closer to the Sun than their present positions, then migrated outward as they interacted with countless smaller bodies. Jupiter may have wandered inward first, then reversed course in what's called the Grand Tack hypothesis, its change of direction reshaping the inner solar system and possibly explaining why Mars is so much smaller than Earth and Venus. Neptune almost certainly migrated outward substantially, sweeping through the primordial Kuiper belt and scattering its inhabitants. Some of those scattered objects still follow highly elliptical orbits that bring them periodically into the inner solar system as comets. Others were ejected entirely, joining the Oort cloud or leaving the solar system altogether. This migration happened relatively early in solar system history, but its effects persist, frozen into the orbital distributions and compositions we observe today. Throughout the solar system, resonances create order from chaos, carving gaps and enhancing densities through the subtle but inexorable power of repeating gravitational tugs. Saturn's rings display this principle beautifully, with gaps appearing where orbiting particles would complete a certain number of revolutions in the time it takes a moon to complete its own orbit. The repeated gravitational nudges from the moon at the same point in each orbit eventually clear particles from these resonant locations. The Kirkwood gaps in the asteroid belt arise from similar resonances with Jupiter, creating empty zones at orbital distances where asteroids would be repeatedly perturbed. In the Kuiper belt, Neptune's gravitational influence has created a population of Plutinos, objects including Pluto itself that orbit twice for every 3 times Neptune completes its journey around the Sun. This 2 to 3 resonance protects these objects from close approaches to Neptune, allowing them to survive in what might otherwise be an unstable region. Resonances also heat moons through tidal flexing, as the varying gravitational forces during their slightly elliptical orbit squeeze and stretch their interiors, generating warmth that can melt ice and drive geological activity. The surfaces of worlds throughout the solar system bear witness to continuing violence, the scars of impacts both ancient and recent. Earth's atmosphere shields us from smaller projectiles, burning them up as meteors before they reach the ground, but larger objects still strike with devastating consequences. The impact that likely killed the dinosaurs 66 million years ago was far from the last major collision our planet has experienced. The Moon, lacking atmosphere or geological activity to erase the evidence, preserves a record of bombardment stretching back billions of years. Mars shows fresh impact craters that weren't present in images taken just years earlier. Jupiter's atmosphere occasionally displays dark spots where comets or asteroids have plunged into its clouds, their explosive demise releasing energy equivalent to millions of nuclear weapons. The frequency of large impacts has decreased since the solar system's violent youth, when planetary formation was still underway and debris filled the space between worlds, but it has not ceased. Every planet and moon remains vulnerable, their surfaces subject to modification by the random arrival of impactors. These collisions do more than simply excavate craters. They can blast material into space, redistribute surface compositions, generate heat that melts and reforms rock, and in the most extreme cases, alter rotation rates or even knock moons into new orbits. Our exploration of the solar system, accelerating dramatically in the past few decades, continually surprises us with complexity we didn't anticipate. Scientists expected Jupiter's moon Europa to be interesting because of its suspected subsurface ocean, but recent observations suggest its surface might be far more geologically active than imagined, with chaos terrain and potential plume activity. Saturn's moon Enceladus, once thought to be a frozen, inactive ball of ice, shoots geysers of water vapor from its south pole, material that feeds Saturn's E-ring and provides direct sampling of a subsurface ocean. Titan, Saturn's largest moon, revealed itself to have rivers and lakes of liquid methane and ethane, weather patterns, and complex organic chemistry occurring in its thick atmosphere and on its surface. The dwarf planet Ceres surprised observers with bright spots that turned out to be salt deposits, evidence of briny water reaching the surface from below. Mercury, studied in detail by the Messenger spacecraft, showed evidence of past volcanic activity and a magnetic field generated by a partially molten core, neither of which simple models had predicted for such a small world. Each mission, each improved observation, each new dataset reveals that our solar system is more varied, more active, and more fascinating than our theories suggested. The solar system's evolution is not complete. The story that began 4.5 billion years ago in a collapsing cloud of gas and dust continues to unfold. The sun will grow brighter and larger, eventually swelling into a red giant that may engulf the inner planets. When we look up at the night sky, we're witnessing not a completed masterpiece but an ongoing performance, one that began billions of years ago and will continue long after our species has faded into cosmic history. Consider for a moment the audacity of human exploration, the remarkable fact that we have sent emissaries beyond the gravitational embrace of our Sun. The Voyager spacecraft, launched in the late 1970s, are now traveling on paths that will never bring them home. They move through space on what scientists call hyperbolic trajectories, curves that open endlessly outward, never to close back upon themselves. These fragile machines, built by human hands in an era when computers filled entire rooms, now drift through the space between stars, carrying golden records inscribed with the sounds and images of Earth. They are our messages in bottles, cast into an ocean so vast that the very concept of distance loses meaning. New Horizons, a more recent traveler, follows a similar path, its journey taking it beyond Pluto and into the scattered realm of icy worlds that mark the solar system's frontier. These spacecraft escape not through any violation of physics but through the precise application of gravitational assists and carefully calculated velocities. They are, in the most literal sense, achieving what was once pure fantasy, leaving behind the sun's domain to wander the galaxy itself. The journey of New Horizons brought us face to face with wonders we could scarcely have imagined. In the cold darkness beyond Neptune, where sunlight arrives as little more than a bright star in an eternally black sky, this spacecraft encountered an object named Arakoth. The name comes from a Native American word meaning sky, a fitting designation for something so distant and mysterious. What New Horizons revealed was extraordinary, a contact binary, two lobes of ancient ice and rock gently pressed together like a cosmic snowman. This shape tells a story of gentle collision, of two objects meeting in the early solar system with such delicate speed that they simply nestled against one another rather than shattering into fragments. Arakoth is a messenger from the dawn of planetary formation, its structure preserved in the deep freeze of the Kuiper Belt, unchanged for more than 4 billion years. The reddish hue of its surface speaks to organic compounds transformed by eons of radiation, while its smooth, nearly craterless appearance suggests it formed in a relatively calm environment, where planetesimals accumulated through gentle touches rather than violent impacts. Our understanding of what constitutes a world continues to evolve as our instruments grow more sophisticated and our surveys of the outer solar system more complete. 9 dwarf planets are now recognized, each with its own character and story. Pluto, once considered the 9th planet, now leads this category of intermediate worlds. Eris, discovered in the early 2000s, sparked the debate that led to the creation of the dwarf planet classification. Makemake and Haumea orbit in the distant Kuiper Belt, their surfaces marked by methane ice and stretched by rapid rotation. Ceres dwells in the asteroid belt between Mars and Jupiter, close enough that spacecraft have orbited and mapped its cratered face in exquisite detail. These recognized dwarf planets represent only the beginning, the first entries in what will surely become a longer catalogue. Dozens of candidates await sufficient observation to confirm their status, objects so distant and dim that even our best telescopes struggle to resolve them as more than points of light. Each discovery adds depth to our census of the solar system, revealing it as far more populated and diverse than earlier generations could have imagined. The solar system does not exist in isolation, sealed off from the universe beyond. It breathes in and out, capturing material from interstellar space while simultaneously ejecting its own substance into the cosmic void. Comets occasionally arrive from trajectories that suggest origins in other star systems, their compositions carrying clues about the chemistry of distant stellar neighborhoods. Meanwhile, powerful impacts on planets and moons can blast rock and ice into space with such violence that fragments escape entirely, becoming meteoroids that wander the galaxy. Some material from Mars has landed on Earth in this way, Martian rocks that made the journey across space without benefit of any spacecraft. The solar wind, that constant stream of charged particles flowing outward from the Sun, pushes against the interstellar medium, creating a bubble called the heliosphere. But this bubble is not impermeable. Neutral atoms from interstellar space drift inward, mixing with the solar system's native material. Cosmic rays from distant supernovae penetrate deep into the heliosphere, their high-energy particles occasionally striking atmospheres and surfaces throughout the Sun's domain. This exchange of matter and energy means the solar system is not a closed system but an open one, in constant dialogue with the galaxy that contains it. To think of the solar system as static is to fundamentally misunderstand its nature. Every planet orbits, every moon revolves, asteroids tumble through space, and the Sun itself rotates, carrying its magnetic field in a great spiral throughout the heliosphere. But the dynamism goes deeper than these obvious motions. Tidal forces gradually alter orbital relationships. The Moon slowly recedes from Earth, its gravitational pull raising tides in our oceans that create friction, transferring angular momentum and pushing our companion incrementally farther away. In billions of years, the Moon will appear smaller in our sky, and total solar eclipses will become impossible. Jupiter's moons dance in gravitational resonances, their orbits locked in mathematical relationships that pump energy into their interiors, melting ice and perhaps harboring subsurface oceans. The Moon will continue drifting away from Earth, slowing our planet's rotation and lengthening our days. Mars will eventually see its small moons, Phobos and Deimos, reach the end of their orbital evolution, with Phobos likely breaking apart to form a temporary ring system. The asteroid belt will continue to grind itself down through collisions, creating ever more dust. Comets will continue their inward journeys from the Kuiper belt and Oort cloud, some destined to sublimate away entirely as they make repeated passes near the Sun. The giant planets will continue their slow orbital migration, subtle but inexorable. Perhaps billions of years from now, Mercury might be ejected from the solar system entirely through a resonance with Jupiter, or Venus and Earth might experience a near collision that dramatically alters both worlds. These are not certainties but possibilities that long-term simulations suggest could occur. What is certain is that change will continue, that the solar system we observe now is merely one frame in a very long film, and that the cosmic forces that shaped its past remain active in its present and will determine its future.